Great. So thanks for inviting me to talk here. So my name is Martin. I'm co-founder and product manager at Luceda Photonics. And so I will talk about photonics and how open access and how they work together. So first I will give a very short introduction on Luceda. Then I will talk about open access and photonics, and then some of the challenges and opportunities that we see in the context of using these two together. So I hope by the end of the presentation, you learn something about how we use open access to exchange photonics design data, highlight some of the workflows that we have, and what challenges that we had. So there are a large variety of applications enabled by photonic integrated circuits, PICs we call them, ranging from the datacom to telecom to sensing in different types of biosensing, LiDAR, quantum computing, and so forth. And so all of these, they require photonics-aware design tools. And that is why about 8 years ago, we launched Luceda Photonics as a spin-off of the University of Ghent and IMEC in the VUB. And we make a software product called IPKIS. And the eventual goal or vision is that we can help these photonic IC designers to have the same kind of first-time right experience as you expect in electronic IC design. So we have 2 locations, our company. So one is in Belgium, one is in Shanghai. This was just a picture from a recent anniversary of our company, like a few months ago. And yeah, these are some examples of realizations done using IPKIS. And so this is a LiDAR application with an optical phased array. This is a datacom application with modulators. This is a quantum key distribution example, some lab on chip, and then some radio RF application. So these are the type of designs that we make with our software. And of course, you also need to be able to manufacture these in foundries. And so in order to do that, we collaborate with several foundries so that you can actually manufacture the chip. So what is our history with open access? So in 2016, we started a collaboration with Tanner EDA before it was acquired by Mentor, before it was acquired by Siemens. And then we launched our first OA-enabled products. In 2020, we did a major refactoring in our code base to enable better interoperability with IPDK and PyCells, some performance and stability. And in 2020, we added Python 3 support to IPKIS and also to OA scripts. Okay, so let's talk about photonics. And so I first would like to quickly show how a photonic integrated circuit looks like, and then how we can bring that to a OA-enabled design tool, and then what things can we do with it in IPKIS. So photonic integrated circuits, I will work mostly on this example today. So this is a multiplexer. So it has 2 inputs and 2 outputs, as you can see, and this is a frequency domain simulation. And you see that it actually generates 2 different channels at different wavelengths. So you could have a broadband input signal from an optical fiber, and then at the output, you can have these channels split up into. These things are also heated. So you have some electrical signals here in order to fine tune the spectrum. And so the way that we work in IPKIS is we are going to define parametric cells, and we do this in Python. So IPKIS is a Python framework. And so later when I talk about OA script, we'll definitely get into the Python OA script domain. So here we have a multiplexer. It can have multiple parameters. And then when you change the parameters, you can actually rerun your design and resimulate it. So let me see. Can you see this browser window?
Yes.
Okay, great. Yeah. So here's a short example. So I have this device here with a specific free spectral range, and I can visualize this. I can have a look at the ports. So you see there's optical and electrical ports. And then I can also run a simulation. So here we run a frequency domain simulation. Whoops, I should make sure to run everything, of course. And then you see the spectrum. So now the next step is to do actual place and route in a open access enabled tool. So I should be sharing Edit now, if that's okay. So
we see your editor.
Yeah, you can see it?
Yes.
Okay, great. then I'm sharing all the screens that I need. So here I'm going to take this cell and I'm going to drag and drop it in the canvas. You can see that it's parametric, so I can change the free spectral range, and you will see that you get different versions of this same multiplexer. And so in the background, IPCIS is running. And so how does that work, actually? So within IPCIS, we define these parametric cells. For example, a direction copper, a multiplexer. We store them into a OA database through a export, and then we bring them into a OA-compatible EDA tool. In this case, we're looking at the layouts. So what I just showed was I'll edit, we drag and drop a cell. So another question is, how does this EDA tool know how to evaluate the cell? And the answer to that is by using P-cell evaluators. So we use the standard OA infrastructure and the OA P-cell CPP gen plugin in order to go back to IPCIS, evaluate the cell in IPCIS, get the layout data, and bring them back into the OpenAccess enabled tool. So that's what's happening here. I can drag in another cell. I can change the free spectral range or the center wavelength, maybe slightly different center wavelength. And here we go, and we add these designs. So now if you want to make this design more complex, we can also do some routing. So actually we want to make waveguide routes. So, and we do so by connecting these. And then we have a waveguide menu, which allows you to generate these optical waveguides. So light is coming on the left, it's going through this filter, then it will be split into two, and then join again into different filters. And you would go on like this until you end up with a final design. So this is the final design that the user makes. So here there are grating couplers. So these are elements which allow you to take a fiber, an optical fiber, shine light basically on your chip. It will be captured and then guided into the structure. It will be split into multiple parts and then here sent to the outputs. So that is the layout realization of this one input for output filter, optical filter, let's say. All right, so now what else can we do with this design? And this is where we will go into the region of OA script and IPCIS. So here, I'm just going to continue in Python. So this is a notebook which allows you to interact with Python codes in an interactive way. And here we have OA script loaded. So this is a recent version of OA scripts that we compiled. And then we're going to load this design. And then you can do anything what you expect to be able to do in OpenAccess in OA scripts, such as checking whether this design is valid. I can open the hierarchy, which will actually do the P-cell evaluations and calculate the full layouts. And then I can go on and start navigating. So this is where Lark's prototype would be very helpful because then I could easily navigate and go around. So one thing that is interesting also to notice that OA script is relatively low level, you could say. So it allows you to do a lot of manipulations and work with the database. But there are some things that would be interesting to be able to do. And actually, IPCIS is very well suited for that. So IPCIS originally comes from the photonics domain and the photonics markets. So it was originally built to make photonic designs, but in fact, it's OA compatible, so we can also load OpenAccess designs. So what we're doing here is we're going to take this cell, this top cell we made in edit, and we can do a visualization. So this will visualize your design within Python, actually. Or what we can also do is we can write a GDS so that you can go for manufacturing. So what else can we do? We can do electrical and optical netlist extraction. So in terms of verification, Luceda actually has a lot of verification capabilities, which are focused on the photonics domain. So one of the things we can do is we can have a look at the netlist view and then print the netlist. So this is going to go through the whole layout and it's going to check for the optical connections and list them here. So here you see the instances. So these are the different designs, the waveguides, the fiber couplers, You see here also the terms, which are a mixture of optical and electrical terms, and then the nets. As you can see, this is quite a big list, so it's a bit hard to really visualize. But what you can also do is then export a SPICE file from this netlist. So here I can look at the SPICE file, and this could then be used for LVS purposes, let's say. And then the other thing you can do is also extract the electrical nets. So typically in the optical circuits will be relatively simple in terms of electrical nets. You might have at maximum 2 metal layers. So the electrical part is actually relatively simple, I would say. So what else can we do? We can also run a simulation on this design. So we start again from this layout in OpenAccess. We're going to load it inside IPKIS, and then we can run a full simulation. And here, okay, if you're a bit aware of how this optics filter should work, it's actually easy to see that there is a mistake in the design, because you would expect these channels to be interleaved. So you would expect blue, orange, green, red, blue, orange, green, red. But in this case, they are interleaved. So there is some mistake in the parameters of the design. And what we can do is we can actually fix them here. We run a simulation, and then we see that the channels are actually interleaved, which is what we expect. A final thing you can do, and then that will be the last part of the demonstration, is fixing sharp angles. So in the optics domain, you see there are a lot of curvilinear features or curved features. And you see here, for example, there is a sharp edge, and foundries don't like this typically. So we need a way to fix this. And within IPKIS, we have functionality to detect these sharp angles and to fix them. So when you would run this, you could actually have a look. Here's the final design. And if we zoom in, you might see these fixes applied to your design. So those were the 4 things that I wanted to show. So maybe a quick word still on some challenges that we saw. So these things I showed. So some challenges, one is more from the software perspective, let's say. So as a company, we provide OA scripts, and we have to compile OpenAccess and some infrastructure. So in the past, we've been dealing with OpenAccess 22.50 and .60, but also 2 versions of OA scripts. And since recently, we also compiled that for Python 3.8. And also we want to support both the Linux and the Windows platform. So that kind of makes the matrix of combinations bigger. And then you have different compilers. So of course, this is not a full dense matrix, but you can see where this is going. This can be actually quite challenging in order to support. So especially over time when versions change, this is one of the things we spent quite some time in trying to compile it correctly for the platforms that we support. And then a second challenge is we had to do some extra information to the OpenAccess database. So just like what Ben Hofer also discussed with OX Color, by using some additional things that you add to OpenAccess. So we did something similar for adding photonics domain information, let's say. So we added port angles and waveguide cross sections on ports as additional information using FDEFs. So that's one thing we did in order to be able to support this netlist extraction and so forth. Curvilinear features is something which is not natively supported in OpenAccess, and so like arcs, shape arcs, and so forth. So we go around this by discretizing using our own discretization filters, which we know work well in production because you have all these curved features. And then another challenge, which is less related to OpenAccess, but also very interesting in the photonics domain, is how do we store S parameters? So imagine you have a multi-mode 50-port device, then you might have a 50 by 50 by 1000 matrix, let's say. So if you have to store that in a touchstone file, you get the gigabyte files. Whereas usually you're not really interested in knowing the coupling between all of these ports. So you could represent this as a sparse matrix, but of course that's not something which is generally standardized. So those, I would say, are also opportunities for standardization, I would say. And so one is the ports, how we define them, and what optical information we need to add, like additional features in the curved domain, let's say, and then the S parameters. So I thank you for your time and welcome any questions.
Hi, Martin, this is Vic. Quick question is, how sensitive are the optical elements to temperature distribution of the system?
Very sensitive. So I can give you the small example I showed here. So the reason why there are heaters on these elements is because you need to be able to tune them in actual operation. So, and by tuning them, these spectra will shift. And this is one common challenge, let's say, in optics, that everything is very temperature sensitive. So you have to either cool or have a very stable environment, or you have to fine tune using additional electrical signals.
Yeah, I've seen some of the examples of recent systems almost going into literally hundreds of watts. So I was just wondering, how do you take into account all this? So thanks for the explanation.
Yeah, indeed. Yeah, so indeed, you need to be able to manage that. So one way to work with it is by very carefully designing these things. So there are techniques that you can do to make athermal designs by very carefully playing with how you design these things. That it is possible, and then you can reduce the temperature sensitivity. But it's a hot topic, if you could say it that way.
What are the primary markets for photonics today?
Yeah, so the primary today is datacom, telecom. Those are the primary. And let's say the ones that are upcoming are the sensing applications. So like being able to build a lab on chip where you can do measurements of diseases or infections, and then LiDAR. These, I would say, come second. And then after that, it will be time for more quantum computing and artificial intelligence, I would say.
All right, other questions? Well, thanks, Martin. And